Hi, my name's Kristen Fletcher, and I'm the Programs and Engagement Manager here at the Haley Public Library. Tonight's talk will be Our Water, the Wood River Valley Aquifer, and Drought with Dr. Jim Bartolino, U.S. Geological Survey's Groundwater Specialist for Idaho. Jim will discuss the Wood River Valley Aquifer, what it is, what we know about it, and how it responds to climate. This is the first in a series of talks exploring our above and below ground water, Idaho law, and how it impacts the Wood River and Valley communities. And as many of you are aware, I'm sure that Blaine County has been designated in extreme drought. People have said that Silver Creek is at the lowest they've seen in more than 30 years. And there are some important sort of administrative discussions going on in terms of who gets water when and for how long if we don't get more water in our system this summer with timely rains, etc. So I always like to suggest a couple of books we have here at the library. One is a oldie but goodie. It's called Cadillac Desert by Mark Reisner. It was written in the late 80s, so some of it's a little dated, but it's got some very good information in it, and it's well written. Another book that came out in 2017 is Where the Water Goes, The Life and Death Along the Colorado River by David Owen. It's a close examination of all aspects of that river and its water. I will also be sending out a list of books that Jim recommended to me, and so that will be in that email that I'll be sending folks who signed up. So let's see. It is my pleasure. Let's see, let me catch this one person. It's my pleasure to introduce Jim Bartolino. He received his PhD in geology and civil engineering from Texas Tech in Lubbock. He has been an hydrologist for the U.S. Geological Survey since 1991. He shared with me just a few minutes ago that he has been 31 years with the USGS, and this is his last public presentation in that capacity. So we're pretty honored to have you here, Jim. So he has worked with the U.S. Geological Survey since 1991 in Austin, Albuquerque, and finally in Boise. He is a project chief and the groundwater specialist for the Idaho Water Science Center. His current projects are a hydrogeological framework and groundwater flow model of the Treasure Valley and assistance with a hydrogeologic framework of the Big Lost River Valley. He has worked on the other groundwater characterization studies, including the Wood River Valley of Idaho, the Spokane River Rathdrum Prairie Aquifer of Idaho and Washington, the East Mountain Area of New Mexico, the Middle Rio Grande Basin of New Mexico, and areas of Iraq and Ethiopia. He has about 80 scientific publications and currently lives in Bellevue with his wife and 3 Chesapeake Bay retrievers. So I am delighted to introduce Jim. And Jim, you will need to mute yourself. I'll put you on spotlight now. Great. So I think you're good to go.
I think I'm live. Okay. Well, Kristen asked me to talk about the aquifer system and some about how it's being affected by drought. I'm taking the approach that I'm going to talk about what the aquifer is, how it's connected to surface water, and then go on and touch on the climate stuff. Looking at who's on the phone, I know quite a few of you, so please keep me honest if necessary. Okay, let's see. Okay, now that's interesting. What does the USGS do? I like to start with this. A lot of people know us from our topographic maps, but really aren't familiar with the other parts of the USGS. We were established in 1879 as kind of an outcome of the 4 Great Western Surveys. So we were set up to collect, analyze, and publish reliable, impartial, and timely science information to enable informed decision making. So in those early days, it was primarily related to mining and minerals. We have early reports on the Wood River district, and it's got maps of the Many More Mine, for instance. But in 1889, Congress asked us to take on water as part of our mission as well. With that, what it's almost important what we don't do is what we do. We don't manage any public lands. We don't have any regulatory responsibility or authority, and we don't make policy recommendations. So we're not like the EPA. Our job is just to do impartial science. So for that reason, people come to us because we don't have a dog in the fight. Our data primarily takes two forms. There's hydrologic data like stream flow and that kind of thing, water levels, water quality, as well as various and assorted interpretive reports. A key part of the USGS when they set us up, at least the water part, was the cooperative matching program. Congress didn't want us going out and just doing irrelevant science. So basically, they only gave us about half of our budget, and we're supposed to use that money and go out and cooperate with state and local governments to do relevant science addressing water problems that matter. So again, I think that was a very wise decision because it keeps us from doing too much interpretive stuff. Well, how we got here. The USGS became involved in the Wood River Valley in 2004 because there were concerns about development and whether the valley had the water resources to support that development. Does this sound familiar? I don't have time to go into some of the people responsible for that. Some of the people on the call right now were involved in that. So what we did is responded to their need to provide data to their decision makers and their resource managers so they could make reasonable decisions. Kind of in the background, which really wasn't relevant for the first part of the study, but I think everybody knew that eventually a groundwater flow model for conjunctive management and administration was going to be needed. But first off, that was kind of in the background. So we came up with a work plan, and the work plan had 4 phases. The first, each with a report. So the first phase was to gather the hydrologic data that we had over here, look at trends in groundwater levels and look at trends in surface water flows. We put together several water level maps of the valley, which hadn't been done for a long time. So we published that in 2007. In 2009, we put together a groundwater budget, basically quantifying the inflows and the outflows from the aquifer, and I'll talk about a budget later on in more detail. The third part was putting together a hydrogeologic framework of the aquifer system. And what that entailed was basically looking at drillers' logs. We did a little bit of superficial geophysics and came up with basically the size and the shape of the aquifer and the subsurface and what the hydraulic properties were. So we published that in 2012, and then finally in 2014, because there was some concern about whether the aquifer system had a problem with nitrate. A lot of the classic elements were there for areas that had nitrate problems, like septic tanks and livestock and that kind of thing. But what we found is researchers before us had found that there really was not a nitrate problem. So that ended our original cooperative agreement with the various cooperators in Blaine County, whom I'll identify later on. And in 2012, IDWR came to us put together this groundwater flow model that they were going to need to manage and administer water rights in the Wood River Valley. So let's start by talking about the aquifer, what it is, how groundwater works, and how the aquifer is put together. This first map, I don't really worry about the colors much, but this is the extent of the aquifer as I defined it in the framework report. Now notice that it goes all the way up here to Baker Creek. We have wells up here at those cabins up in Baker Creek, but by and large, we really don't have any information from here to here. So the Frostbite Flats area and in there. So basically for the groundwater flow model, we cut it off here at this, at the confluence with the North Fork of the Big Wood River. So what the aquifer, how the aquifer was formed is that you had the ancestral Wood River Valley that flowed down this long valley and came out into this broad area that's the Bellevue Triangle. Now, a lot of these canyons up here had glaciers in them. You can still see glacial moraines in some of the canyons off Baker Creek. So basically, for several 100,000 years, you had the ancestral Wood River Valley flowing down and carrying sediment down from these glaciers and just generally from erosion. So the Big Wood River came down into the triangle, and it would flow this way for a while, and then it'd build up its bed and then flop over here and then flop over here and then just flop back and forth. During the glacial periods, you had more water, so coarser material was carried down. During the drier interglacials, finer grain material was deposited out here. So eventually what happened is over time, you built up an alluvial fan down here. I'll come back to this in a minute, but all of this are sands and gravels lying on top of granitic and sedimentary bedrock. All this area over here that's cross-hatchered, this is the extent of basalt in the subsurface, and I'll come back to that in a moment. So the thickness of the aquifer varies. This is a map of aquifer thickness. The deepest part of the aquifer is down here in the middle of the triangle. Here's Gannett, and this is Baseline Road. And you can see that the aquifer is about 350 feet thick down here, but over most of the aquifer, it's much, much thinner. So this is what the aquifer looks like. This is a gross simplification, but this is more or less what it looks like in cross section. So underneath we have this bedrock, which again is granite from the Idaho batholith, and those are the granitic rocks we generally see on the west side of the valley, and also these older sedimentary rocks, typically these dark shales that you see up in the Pioneer Mountains and in the side canyons. But the aquifer itself is this alluvium lying on top of that. And this is composed mainly of sand, gravel, and clay. In that area in the last slide that we looked at, where there was basalt down there on Silver Creek towards Peekaboo, a lot of wells down there are completed in basalt, but for the most part, the wells in the valley are completed in this alluvium. Okay, so our thickness, as I mentioned, is about 350 feet in the lower valley. In the Ketchum area, it's ballparkish around 100 feet. In the upper valley above Ketchum and some of the larger tributaries, your aquifer kind of is maybe in the 20 to 30 foot range. And as you get further up those tributaries or in the smaller tributaries, sometimes you have less than 10 feet of this alluvium laying on top of bedrock. So the aquifer is very thin in these side canyons. Okay, so what are the water
Jim,
levels?
could I interrupt with just a real quick question? Someone asked if there's an ideal depth for an aquifer.
There's not.
Okay.
And I will, later on, we'll come back to that, and I'll tell you why it really doesn't make any difference how thick our aquifer is. I mean, except in the side canyons, but it depends on how productive it is. But in the Wood River Valley, the thickness, at least in the main part of the valley, is kind of irrelevant. And I'll come back to that. It's a
Okay,
good
great.
question.
All right, thank you.
That's a good question.
Mm-hmm.
So the way the water in the aquifer works is in most of the valley above, say, baseline road, we've got just a simple water table aquifer. That means that the water basically is just sitting in the sands and gravels directly connected to the surface. So when you drill a well in this, the water level rises to that water table level. Well, starting at baseline road, actually, let me go back a slide. I'm sorry. So we had the big Wood River flowing down the valley and depositing these alluvial sediments down here. Well, at some point we had volcanic eruptions and it deposited all this basalt over here, and it also deposited basalt over here, which basically dammed the outlet of the big Wood River. So we had a lake form. We had a lake form down here. Well, as we all know, we get silts and clays deposited in lakes. So basically, for a while, you had sands and gravels deposited above this lake, but this lake was putting down these clays and silts. Eventually, the Big Wood River eroded its way through these basalts, and the lake drained, and you continued to deposit sands and gravels on top of that. Okay, so going back, I apologize. Starting at about baseline road in the subsurface, this is where those lake sediments start. So we have the original alluvial fan deposits below it. Then we have these lake clays and silts, which are fairly impermeable. And then above that, you have the unconfined aquifer. Okay, so the water levels, the depth to water in the unconfined aquifer goes anywhere from basically land surface at the streams down to maybe 100-foot depth in places. So in beneath this confining bed, we have the confined aquifer, and water levels wells that are completed in the confined aquifer, basically these are flowing wells. So water actually rises above the land surface. So how does that work? Again, we drill a well in the unconfined system. Water level is 10 feet below land surface. Basically, the water level in our well rises to 10 feet. But in the confined system, where we start here, hopefully everyone else is not cut off by the participants like mine is.
We can see it just fine, Jim.
Okay. So starting here, all of this water in this lower confined aquifer is at the head or pressure, basically where that confining bed starts, and it's under pressure. So when you complete a well in this lower confined aquifer, the water level in that well wants to rise to that surface. Because the well is not, if we built the well all the way up there, the well would stand in the water would stand in that well, but most wells aren't. And so we have these wells that actually flow down in the triangle. And there's quite a few artesian wells down there. I hope this makes sense. If we need to come back to this, we can. That's the bad thing about Zoom presentations, is that it's really hard to read the audience to see if you all have blank stares. Another character of the aquifer system is that it's really well connected to streams, both Silver Creek, the Big Wood River, and then some of the side canyons like Warm Springs or Trail Creek. Okay, in these side canyons where the alluvium is so thin, sometimes these wells where the saturated thickness is so thin, basically well drillers will drill a well down into this bedrock below it. There's a little bit of water down in this bedrock. There isn't much. I think for the most part, these wells are deepened to have some well bore storage for really low producing wells. Okay, so what do water levels look like in the valley? Well, We have 3 wells that the USGS started measuring in 1954. This is a well that's a flowing well just north of the rest area and the blinking light. Okay, because this is an artesian well, the numbers are in height above land surface. So that's the pressure head. If we completed a well to 50 feet, basically above land surface, that's where the water would stand in these wells. So starting in 54, we can see this well. We can see an annual signal, as you would expect, irrigation season, non-irrigation season, and it kind of goes back and forth. The water level drops during dry years. During dry years, aquifers kind of get a double or a triple whammy. First of all, they're getting less recharge. And secondly, as people's surface water runs out, they tend to pump more groundwater. So you get this kind of double hit. So, but anyway, you can see this annual signal, and then you see these longer droughts or wet periods. Okay, dry, and then it kind of recovers for a few years and it drops back down. So eyeballing it, most of us would go, that thing looks like it's declining. That's declining. Okay. This is another well. This is a water table well near Gannett. This is depth below land surface. Again, we see this annual signal up and down. We see these drier years, and we see it recovers during the wet years. Again, this kind of goes on, dry years, really dry years. But again, it recovers. But again, if you look at this thing over time, this one's a little harder to see, but it's like, yeah, that one looks like that's probably declining over time. Okay, here's a third well that we've got record from the mid 50s, and this is a well just south of Bellevue. Again, this is depth below land surface, and this is 30 feet to 60 feet. So again, we see this annual signal. We see these dry years. We see the recoveries, and then it kind of drops down, and we see these really dry years in about 2015 and such. Okay. Again, again, this one is even harder to see. I'd say that one's declining. This is a well in Warm Springs. It was measured for the first time in about 86, and then it wasn't measured again until 91. So if you ignore this, sure, it'd be nice to know what water levels we're doing in that period. I think this is probably a bad water level, but it'd be interesting to see what would happen. So that's why we need to do long-term monitoring. But again, this one kind of pokes along. It's really hard to see what's going on with that one. And finally, there's a well that's south of Highway 20 on Silver Creek. It's kind of down off the Peekaboo Desert Road. Again, we've got data since the mid 50s, and you see kind of the same pattern. Okay, so in 2007, when we did that first report, rather than just eyeball these things, we did some statistical analysis, and we did it on the 3 wells, not the Warm Springs well that we had the 50 years of record. And doing statistics on it, we could see that all had statistically significant declining trends in water levels. Okay, so the human eye loves to find patterns, but if you look at this statistically, there's no doubt that there are declines in these wells over a long period. The other thing we can take away is that we see these things are very influenced by precipitation. They'd go down in a hurry, they come back up in a hurry.
Jim, a quick question about reading your graph. From our view of it, the line on your graph, some of the lines themselves are thin and some of the lines themselves are thick, like it goes from a Sharpie fine point to a Sharpie medium point. Is there any significance in that thickness of the line that we see in your graphs?
There is, Kristen, and that's a good point. Okay, I am honest most of the time, and whenever I plot data, I always like to show the data points. So basically, where the line is thicker, that means we have lots of water level measurements. And here for a while, there were continuous recorders in some of these wells for a while. That's where you see the really thick lines. But at times, this particular well was measured every 2 weeks. Later on, it would go, to monthly or maybe twice a year. Sometimes it might only be every year. So you can see it kind of pokes along. And then back in about 2012, IDWR put water level transducers, which record the water level. I think they were probably hourly punches. So there's a lot more data points on these. So that's why it looks thicker. Never trust anybody that doesn't show their data points on their graphs. Okay, so we reanalyzed this in 2014, and those two wells that I didn't look at before, one because it was outside the area and one because we didn't have enough years of data. I reanalyzed these things statistically, and I used a little more sophisticated statistics than we did the first time around. And the original 3 wells plus that well south of Peekaboo all show declining trends. And again, it doesn't make any difference if I looked at it seasonally or annually or however I tweak the analysis, those were all declining. The Warm Springs well, however, has a statistically upward trend. I don't know why that is. It could be because it's so close to Warm Springs Creek would be my guess. It's not far from the dog park, old golf course. So that may well be what's going on there. Okay, so I'm going to skip from the groundwater system and talk about surface water. Well, the USGS first started measuring surface water stream flow in the Wood River Valley in 1889. Now, we were only tasked with measuring water in 1889. So this is one of this 1889 measurement from Haley. That's one of the very first water level or stream flow measurements made in the United States. So basically not much happened in the intervening years for various assorted reasons. But in 1915, we put in a long-term gauge at that Big Wood River at Haley site. So from 1915 to the present, we basically have continuous stream record. Now, one thing that you have to watch, if you look at the monthly statistics and the annual statistics, basically in those early years, the Haley Slough paralleled the Big Wood River, and they ran water into that Haley Slough to power the hydroelectric plant that provided power for Haley. So there were actually 2 USGS gauges at this location in those early years. So when you look at the statistics, the long-term statistics, they factor in both stations. But if you go in and start looking at the daily data, you have to look at both stations. So, be careful if any of you go back and start looking at some of that old data. So at any rate, this one since 1915. There was another gauge, long-term gauge. This was at Stanton Crossing. This gauge used to be downstream. Again, if any of you guys go back and look at this, the original gauge was downstream just below the confluence with Willow Creek. And Willow Creek pulls in a lot of this area south of 20 and comes into the Big Wood down here. Well, when Magic Reservoir was full, we felt that we were getting some backwater effects at this gauge. So I think it was 1996 that we moved that gauge up to its present location there at right beside the road at Stanton Crossing at the bridge. So the other long-term continuous gauge we had was this gauge at Sportsman's Access. That's the one that was on the title slide. This gauge used to be down here by that long-term well that we were looking at. It was discontinued. I think it was in the 60s, and then they restarted it in the 70s up at its current location on Silver Creek, just above 20 up here. So at any rate, we had these 3 long-term gauges. Well, when IDWR started looking at doing a groundwater flow model, it dawned on all of us that this wasn't nearly enough surface water data to do a model with. So starting in 2010, with funding from IDWR in District 37, we started installing new gauges up here. The first of these was this gauge. It's titled Near Ketchum. This is right here at SNRA headquarters. This gauge was run from the 40s into the 60s, or maybe it was the 80s, and then we reactivated in 2010. We put a gauge. There'd never been a gauge in the North Fork of the Big Wood River just before it comes into the Big Wood. Early on, we installed a gauge on Trail Creek just above its confluence with the Big Wood in Ketchum. A few years later, we came back and added another gauge up here near Boundary Creek Campground. We put a gauge in on Warm Springs Creek. Again, that's right there at that bridge that crosses to the old golf course dog park. And then just last year, I think it was, we put another gauge in up here at Gates Road, right there where near where the parking is for Warm Springs ski area. We put a gauge in on the East Fork, probably about a mile up for when it hits the Big Wood River. And then we added a gauge. Again, this was just a few years ago at the Big Wood River Bridge in Bellevue, right there where Broadford Road crosses it. So, right now, and all this is to give us data for the groundwater flow model. So right now, the Wood River Valley is probably the most instrumented basin, certainly in Idaho, and one of the most in the United States. You can get to I'll come back to this. You can get to this real-time data at this URL. Okay, so if you click on that URL and go, it gives you a list of stream gauges in Idaho, and you click on a gauge, and this one is actually the Big Wood River at Haley total flow. It brings up this page. Now, most of you that fish and the boaters, know these sites and they use them well, use them a lot, but the general public tends not to be very aware of them. So you click on this page and you can get 3 parameters. There's water temperature, there's stream discharge, and there's gauge height. You can control the period for which you're looking at the data. The default is 7 days, but you can make this the entire period of record if you want. And then you can see this as a graph or a table. So I pulled this yesterday. So basically, this is the discharge in cubic feet per second, and these are the last 7 days. So here we see the hydrograph, and you can see it's having a diurnal signal. So it goes up and down. It's up at about 1,000 CFS on June 5th, and then it starts dropping down. And then yesterday when I pulled this, it's basically at 600 CFS. Okay, these yellow triangles, that's the long-term mean for that date, for that gauge. So you can see that we're well below normal. So again, boaters and fishermen use these things in different ways. I use this if the Big Wood's above 500 CFS, I don't let the dogs swim. So use it however you want, but it is kind of interesting. And incidentally on this gauge, you can click here, and this isn't for all gauges, but it takes you to the National Weather Service river forecast, and it shows flood stage and all of that, which many of you are familiar with from the past few years.
So Jim, why wouldn't you let your dog in the river if it goes below 500?
It's above 500.
Oh, if it's above 500. Oh, okay.
Yeah, down there in that reach in Bellevue, if I can't stand up in it, I don't trust the dogs. So they like to swim more than they have sense. I don't want to go get them out of the Cove or the District 45 diversion. Okay, so how do these tie together? Well, as we talked about in the aquifer slide, we know in the Wood River Valley that the surface water and the groundwater are very intimately connected. So in a stream, we can have several different ways that it behaves. So if we've got a situation where the water level in the surrounding aquifer is higher than the stream surface, basically water discharges from the aquifer into the stream. So the stream gains flow, and we call that a gaining reach. So stream flow gain equals groundwater discharge. Okay, in situations where the stream is actually higher than the water table in the surrounding aquifer, that stream loses flow to the aquifer. We call that a losing reach. And basically, when we have a losing stream, we end up with groundwater recharge. Okay, there's a third situation where if the water table, typically where the water table is so much lower than the stream that they're not connected anymore, we call this a perched aquifer. Now, usually this is because we've dropped the water level so far, but they can occur naturally if we have, say, a lot of clay beneath the stream. This is what we see up in the Spokane Valley in places. But by and large, it's because we've just pumped the heck out of the aquifer. Okay, we think, we'll get to this in a second, but we think that this is the situation in what are historically called the dry beds below Glendale, the bridge at Glendale Road, where the river's commonly dry and you see that dry stream bed. So we think that basically, even when it does flow, that stream is not very well connected to what's going on in the aquifer. Okay, how do we tell this? Well, we do something we call seepage measurements. Or seepage runs, and basically we identify the gaining and losing reaches and how much water it's gaining or losing. So in 2012 and 13, we measured flow at 50 sites. Now, when we do one of these seepage runs, we do this over a period of a couple days so that conditions are more or less steady. If it starts raining while you're doing measurements, you're hosed. Sometimes if the flow is really low, the differences you measure are so small that it's within the bounds of your error. So what we did in measuring these 50 sites from up here at SNRA all the way down to Silver Creek, and basically what we do is we measure the flow at the upstream end of a reach and the downstream end of a reach. We have to quantify how much water is coming in from any of these tributary streams, diversion water that's going out or coming back in. And basically it's just a big accounting exercise. So what we came up with is this first reach of the Big Wood from basically SNRA headquarters down to about Lake Creek. The river gains flow from the surrounding aquifer, okay? When you get to Lake Creek down to about Warm Springs, that reach of the river loses flow. Hewlin Meadows is in here, and there's various assorted homes and stuff in here. I can't really say for sure why this is a losing reach, but it is. Finally, from Warm Springs all the way down to the gauge at Haley, once again, the Big Wood River gains flow from the aquifer. But below Haley, it's basically that river is losing water in a big way. Now, part of that is during part of the year, right here at Glendale Road, which is going to be about right here, basically, we divert all the flow from the Big Wood. There's a small ditch or canal that goes off onto Poverty Flats, but at the baseline diversion. And the water goes into this baseline diversion, and then, it goes off into canals and stuff on the triangle, but it can be channeled back in on right here, back to the Big Wood River. So this was done in 1921 because they recognized that they were losing river flow in this reach. So the idea was, well, if we put it in a canal, we can get it around this dry section a lot more quickly and get it back into the river. Right here, we have natural springs where the river basically feed the river and the river starts flowing again. So that's why the bypass drops back in here. So, but this basically is a losing reach through here. when the Big Wood starts flowing again, it gains water from the aquifer, Willow Creek, all these little tributaries. And then we have the Silver Creek system, and all these tributaries by and large gain flow. It's kind of interesting that all of these springs and tributaries in the triangle, all of these headwater springs are at about the same altitude across the triangle. It's kind of interesting. I've got some theories about that, but I'm not going to wave my arms. So anyway, these are your little creeks like Stalker Creek, etc. And then the Silver Creek flows down, goes by the gauge, and then flows out of the Wood River Valley down here. Okay, Silver Creek's mostly gains, even though there's some small reaches that switch depending on the season. Yeah, Kristen?
Yes, well, this particular slide has generated several questions. So one person asked about a losing reach, and if there is an association with population in that area. I mean, you kind of implied that maybe Hulen Meadows, maybe not so much, but is there any other kind of correlation?
Well, I'll come back to this in a slide, but certainly, I mean, well, let me get on a couple slides, and I think I'll answer your question, and I'll come back to it.
Okay, two more questions on this one. Let's see, I'm going to have to read this question. A losing reach has water, ? But only coming from upriver to fill the stream bed?
Pretty much all that.
Okay.
In a losing a reach, you have flow from upstream that comes into that reach. So say you measure at the top end of that reach, and it's just, for instance, say 500 CFS, and at the bottom end of that reach, it's 300 CFS. Basically, you've lost 200 CFS of stream flow in that reach. So yes, and if you lose enough flow in that reach, you dry up the stream bed.
Okay, and then so the person who asked about the losing reach associated with population use goes on to say, by my question, I mean, Hulen Meadows Reach has water running through some beds, even though it's a losing reach.
Right. We all know the river flows through there all year long. Basically, though, the stream flow diminishes along that reach. And I'm not pointing fingers at Hulen Meadows, and I certainly that's not my intention. But as far as the well question goes and the population goes, let's look at these next couple slides and see if that answers people's questions.
Great, thank you.
Okay, so where does, thinking about what we've learned so far, where does water come from, in a well come from? Okay, so if we go back to say 1864, when the first people stumbled into the Wood River Valley, the natural system was, and this is just a hypothetical cross section, but say it's down in a triangle, basically a land surface. You had snow, melting snow and rain fall on the land surface. Some of it ran off, but some of it infiltrated through the ground down to the water table. Okay, because nothing else is going on, basically water was flowing and groundwater was flowing through the aquifer and discharging at our streams. Okay, so far so good. All's hunky-dory. Well, starting in probably the 30s, but the big irrigation turbines came in the 50s. We come in and we drop a well into this nice steady state natural system. Once we start pumping that well, the first thing that happens is that we form a cone of depression around the well, and basically this is just water getting sucked into the straw, and basically you get a little bit of kind of we call it a cone of depression. You guys can visualize that, so you can see that it drops down. Well, the original water surface was up here, so basically the first thing we do is we take water from storage. We remove water from the aquifer, but so far we're not affecting how water is moving through that aquifer. Well, if we keep pumping that well long enough, basically we drop the water table a little more, and some of this flow that was naturally going out to the discharging at the streams, we start intercepting some of that flow. And basically what we end up doing is reducing the stream flow some, probably not a bunch, but you know, we definitely are taking water out of here that would have gone here or here. Well, we keep pumping long and hard enough, and we drop that water table long enough, basically we reverse the gradient. So these gaining streams, now they're losing streams. Okay, so we've got water flowing out of the streams and flowing to this well. So basically this well is depleting stream flow. So I think that's what the person was asking is, does development wells have an effect? And yes, yes, it can. I mean, it depends on a lot of things, but by and large, you know, this is where water in a well comes from. So in the Wood River Valley, you know, our streams are intimately connected to the aquifer. So, you know, this is why we're seeing an effect on the streams from pumping, and what some of the issue is on the situation to the south. Okay, Kevin's going to talk about water rights in, I guess, in a week or two. But one thing I'd like to point out is in the West, we have what's called prior appropriation doctrine, or first in time, first in right. So when the West was first settled, basically, you know, this is before we had the technology for wells. First of all, basically the streams were utilized for irrigation. So like in the Wood River Valley, you've got water rights going back, you know, good water rights are 1884 in there for the surface water. Well, when groundwater use started, basically most of the Western states didn't understand how to deal with this. So basically they administered the groundwater rights separately from the surface water rights. Okay, well, a lot of these groundwater rights were, say, 1950. Well, if you get into this situation, basically you have a situation where somebody with a 1950 groundwater right is impinging upon the rights of a 1984 or 1884 water right. Well, this isn't fair. Now, some states never figured out what to do about this. Some are figuring out what to do about it. California is not dealing with it, which is part of the reason that they're in a mess. Well, in Idaho, the decision was made to, obviously, we have to administer all of this as one system. So this is called conjunctive management or conjunctive administration. So what that means is that we're managing all this as one resource, which it is, okay? I'm not going to go much further into that, but you know, we can look at this picture, do fairly simple equations and describe this, no problem. Well, if all of a sudden, you know, we've got 500 wells that we're dealing with and multiple streams and this becomes a lot more complicated. So to do that, we have to go to groundwater flow models.
Could I ask you a quick question in here? And actually, maybe this next section will answer it, but here's the question. Does USGS have a water model that shows the difference between consumptive use, like trees, and household use, like toilets and showers? And kind of along with that, is there a water model for the Wood River Valley?
Yes, there is a groundwater flow model for the Wood River Valley, which I'm going to talk about now. As part of the model accounting, we deal with the domestic wells differently. And if we get to the end, I can go into this in more detail. But essentially, groundwater pumping in itself is not really the issue. It's what is consumptively used on the groundwater pumping. So for instance, on an irrigation well, you put that water with a center pivot or whatever out on your crop, some of that water infiltrates back and soaks into the field past the root zone back to groundwater, but some of it is lost through crop evapotranspiration. The municipalities, they pump groundwater or use spring water. That water, a portion of that water that goes to your house, a portion of that goes onto your yard and is lost as consumptive use. But part of it goes down the drain and back to the wastewater treatment plant. So that water doesn't disappear. I mean, just because you turn on the faucet doesn't mean that water evaporates into another dimension. Finally, domestic wells, you pump the well, some of that water is used in the house, it goes back to a septic tank and eventually ends up back and most of it ends up back infiltrating the groundwater and becoming recharged. And then some of that is used watering plants and consumptive use. A very small part of that water in the house goes to evaporation. When you've got the shower on, the steam, whatever. I have never seen anybody make a good case for what that number really is. I mean, generally we assume it's 1-2%, maybe at most. So I think that kind of answers your question. And for the groundwater flow models, and I wasn't going to go into this much detail, but we use satellite imagery and a satellite processing method developed at the University of Idaho to actually map evapotranspiration, which is the consumptive use. So that's how we can get at some of these numbers that we really can't measure. Okay, at the end, if I didn't answer that, I can show you some pictures explaining that better. Okay, we all know what a model is, especially this last year. It's been population model this, virus model that, blah, 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 blah. Every time we turn on we look at the weather forecast, we are using weather models. We hear about economic models, etc. So basically all a model is a simplified representation of the appearance or operation of a real system. So in our case for groundwater in the Wood River Valley, here's kind of a block diagram of how the system works. Okay, so we've got this lower confined aquifer, we've got this confining bed, and then we've got this upper unconfined aquifer. We have percolation, deep percolation from these agricultural fields. We've got well pumping that goes out to the subdivision, et cetera. We've got a stream flowing through it. We see some water discharging to the stream. So this is how we kind of figure out how the system's working. Well, to build a model, what we do is we attempt to simulate the processes of a real aquifer system by solving a series of mathematical equations. So essentially all a groundwater flow model is a big accounting program. So we construct a groundwater flow model by representing the geology of the aquifer system as a series of blocks. And that's called model discretization, and it looks like this. Okay, so here you can see we've got 3 layers. Here's our confined system, our confining bed, our unconfined system. So we've got a 3-layer model, and we've got all these blocks divided up into rows and columns. So depending on what our study objectives are, that's how we choose what the model code is. So you can think of the model code almost like Excel. Excel is the program, and in the spreadsheet is the data that's in the program. So a model kind of works that way. Whatever the model code is the program, and the model is the data that we populate it with. Okay, so kind of expanding on that discretization, basically, in the Wood River Valley, we've got this unconfined aquifer that's on top. It's sand and gravel. It's got really high permeability and porosity. We've got this confining bed, which is silt and clay, pretty low porosity and permeability, well, permeability. And then the lower confined aquifer is sand. So it's finer grain than the upper one, but they all have different hydraulic conductivity or permeability values. So basically we divide this up into our layers like this and our blocks. So when we put this thing together, this blue line is our hypothetical aquifer outline. So we've got all these cells that represent the aquifer, and all these have got values for hydraulic properties and geology, et cetera. Okay, if we look at this thing in cross section, we can see, well, in this case, it's a 4-layer model, but you can see that we've represented this. So basically all a model is a bunch of stacked blocks. And what a model program does is it just keeps track. It uses the groundwater flow equation, and it keeps track of the water moving into the cell, out of the cell in all 3 directions, and then for this cell, and then this for cell. And so you have your time steps, which may be monthly time steps over, say, 15 years. And it does this for each time step. So basically a model is just a big accounting program. By the way, the Wood River Valley model, I think, is like 450,000 cells. So the computational power adds up in a hurry. So the actual groundwater flow model of the Wood River Valley, we developed this between 2012 and 17 with the USGS, the USGS and IDWR, and we did this collaboratively. And the model code we used is ModFlow. ModFlow was really the first groundwater model. It's a USGS. It's open source. It's free. It's the most widely used groundwater flow model in the world. There's other groundwater flow models. There's solute transport models to model contamination. There are saltwater intrusion models, but ModFlow is just a groundwater flow model. Okay, so IDWR, after the Eastern Snake River Plain model and the Spokane Valley Rathdrum Prairie model, well, during those models, they actually have gone to this process of an open and transparent process, which involves a modeling technical advisory committee. And the modeling technical advisory committees are open to whoever wants to sit in on them. And typically it's stakeholders. This can be consultants working for various assorted folks. It can be people that are water managers. It can be people like Larry Schoen that have a house on Stalker Creek and know how the system operates. So in these MTAC meetings, we typically had them quarterly, and we'd present for how we were going to handle a specific aspect of the model and get input from basically the MTAC. And sometimes it'd be, yeah, Jim, that's brilliant, that's great. And other times it would be, you're too dumb to understand how that really works. Let me tell you how it really works. And so using this process, with these meetings and the occasional field trip, here you can see Pat McMahon being incredibly impressed with how smart my arm waving is, but actually getting out in the field and seeing how these things work and getting the stakeholder input. Now in the MTAC, not everybody got their way on everything. Sometimes it's just like, that's a great idea, but we just can't do that. Or, we think it's going to bias the model if we do it this way. Models are not perfect, but it's certainly better than the old days when somebody gave the USGS a chunk of money and we came back in 5 years and said, here's your model. Things just can't operate that way anymore. So I think it's a welcome change. So what are the intended uses of this original USGS IDWR groundwater flow model? Well, it's a USGS mission to better understand the aquifer systems in the United States. So that checks off one of our boxes and why we're involved. The model can be used for planning efforts. The Idaho Water Resource Board has 50-year water plans for the basins in the state, and this is the kind of thing that can be used as a tool in those planning efforts. And then finally, IDWR wanted something that they could use for water rights administration, and specifically this conjunctive administration that we talked about with the groundwater and the surface water being intimately connected. So the original model that we published in 2017 had a simulation period of 1995 to 2010. So unfortunately on models, at some point, remember I said that we really started putting the gauges in 2010 and started collecting all this new data in 2010. Unfortunately, we have to say, if we're ever going to get finished, we have to just basically say, we're going to do it for this period, get the model up and running, and then later we can go back and add the additional data. So in fact, in 2019, IDWR updated that original USGS IDWR model and with additional data. So they brought the model up from 95 to 2014, and it incorporates all that data we started collecting in 2010. So this is pretty common. I mean, this is how things work in Idaho. We're actually IDWR is in the process of finalizing version 2, whatever, of the Eastern Snake Plain model, and they're starting to think about version 3. So basically, with each of these model versions, we improve our understanding of the aquifer. We get additional analytical tools in the modeling code. Computers get more powerful. So basically, we keep improving these things as we go along. So to finish up, well, part of what the groundwater flow model gives us is a water budget, and this is a water budget for the aquifer. And what this is an accounting of a quantification of the various components of inflow into the aquifer and outflow from the aquifer. So if we look, at least according to the model, of what's coming into groundwater or recharge, losing streams account for 50% of the recharge of the Wood River Valley Aquifer system. Our next biggest component of recharge is aerial recharge, which is this precipitation, this melting snow, the deep percolation of irrigation water through the root zone. Okay, so that's the main components of recharge. If we look at water that's discharging from the aquifer or outflow from the aquifer, most of that water, 71% of it, is through gaining streamflow reaches, which you remember, that's where water discharges from the aquifer. So 71% of the water leaving the big Wood River aquifer system is going to feed Silver Creek and those gaining reaches of the big Wood River we talked about. There's another 18% that's production well pumping. And as I kind of touched on a bit ago, we treated domestic wells differently, but this is production from irrigation wells, municipal pumping, and some industrial wells as well. So between those, that accounts for 89% of the discharge. Some of that is aerial discharge, and this is what the plants that reach the water table drink, things like cottonwoods and some of your marshy areas and that kind of thing. Some flows out underneath Silver Creek. Some flows out in the subsurface beneath Stanton Crossing. And then some of it we have to account for aquifer storage. Now, up here, this third source of water to the aquifer's tributary basin underflow. And this is water that flows into the aquifer from the tributary canyons in the subsurface. This is impossible to measure. So that number is pretty much a guesstimate. And it's the same thing with these two numbers here. And there's ways that we can calculate it, but again, I mean, there's, basically we can make a scientific guess. So with that, I'd like to acknowledge the people that paid for this study. So the original phase that I talked about with the four reports was we paid half of the cost of the study, but the other half of the study was paid for by a consortium of governments and NGOs here in the Valley. So Blaine County was the main contributor, but all of the cities, the Nature Conservancy, contributed money to Blaine County, which was then passed on to us. Blaine Soil Conservation District got the ball rolling in the first place with the initial match. Sun Valley Water and Sewer District, and then at the beginning, there was a small NGO called Citizens for Smart Growth that weren't around a lot of years, but they were one of the original advocates for the study in the first place. And again, you know, several of the people on the phone were part of some of these organizations that helped get this thing going in the first place. So when we got to the model, IDWR paid for most of it, and then Water District 37 contributed to some of the cost of the gauges. So basically, you know, pretty much everybody on this call is a taxpayer to one or more of these entities, as well as a federal taxpayer who's paying for the USGS contribution. So, you know, I think in this case, you know, your tax dollars, you know, helped us get a handle on what's going on. So I'm going to shift gears at this point. Kristen wanted me to talk some about climate and drought.
I do. And can I ask a quick question before then? So Mark is asking, do I understand that consumptive use basically stops during the winter months?
More or less.
Okay.
I mean, when there's 3 feet of snow in the ground, the plants aren't doing much transpiring. Yeah, I mean, there's still some evaporation from ponds or the river that don't freeze over. You know, we lose a little bit or some degree of water from the snowpack. We call that sublimation, where during the winter it goes directly from snow to water vapor. There's huge arguments in the literature about what that number is. Some people think it may be as much as 60%. Some people say it's insignificant. It probably depends. It depends on the basin. It depends on the snow. There's just all kinds of things. So, but by and large, consumptive use more or less stops in the winter.
And then we have a question from William, and I think I'm reading this correctly. Are you saying that climate is the biggest delta to change in the valley? And that may be a misspell, so William may have to type that question in again.
The delta, well, the delta basically is notation for change.
Gotcha. Thank you.
So,
or is that where we're going in this next section?
I will say that we know that the aquifer responds really dramatically to climate. Again, dry years, we see it in the water levels. You know, the more wells we drill, they do have an impact as to whether wells are the major driver at this point. Probably in parts of the valley, yes. But I think for the valley overall, I think climate, drought cycles are probably the main driver. I don't know. I'm not going to go too far out on a limb on that. It acts differently in different parts of the valley. I'm sorry to weasel out of that one. Okay, well, we'll move on to climate. Now, here's the big caveat. I'm not a climatologist. I'm not a meteorologist. I have to use this data in my work, but by no means am I authoritative on this. So I'll try to stay on the safe end of things and kind of talk about climate in the valley. So the first thing I'm going to start off with, where have we been? Hydrologists like to use something called the Palmer Drought Severity Index. And what this is it's a calculation that uses things like soil moisture, precipitation, temperature, season, blah, blah, a lot of things kind of go into this equation. And it's usually calculated over a period of several prior months. So like the March may incorporate data from February, January, and December. So these things are calculated. These things are calculated by a climate zone. Idaho has 10 climate zones. So the two in the Wood River Valley are number 4, which are the Central Mountains. And that's this yellow line, and the Central Plains, the Eastern Snake River Plain, which is this green line. So when you do the Palmer Drought Severity Index calculation, it gives you a number. If that number is positive, the more positive it is, the wetter it is. So anything above 1, you can see this table down at the bottom, is considered wet. Okay. On the other side, as the numbers get negative, that means it's dry. And anything below 1 means that we're getting into drought. So the stronger, or the higher the number or the lower number is from the central axis, the worse, the wetter the period is, or the drier the period is. So the PDSI has been calculated monthly going back to the turn of the last century. So you can see, we've got these wet and dry periods. Often the two climate zones go the same direction. Sometimes they don't. So looks like we have kind of a dry spell here, about 1905, and then we have some really wet years. And we kind of go back and forth and hop around. When we get to 1930, the drought of the 30s, and boom, we start seeing multiple years of drought, and we're seeing very strong. Now, according to this table, anything for this less than 4 is extreme drought. Well, here's the 4 line. So you're seeing that we're having some huge droughts during the 30s. There's a few wet years interspersed. And sometimes the Eastern Snake River Plain got wetter when the mountains didn't, but that's a pretty dry period. So this is one that's it's a famous historic drought. So after the 40s, we kind of go along, and we pop back and forth. Here in the mid 50s, the Central Plains, we have a 5-year period of so where it gets pretty dry. This kind of corresponds to the drought of the 50s, which was really bad in the Southwest, especially in Texas. So going to 1960, I'm going to ignore those for right now. Going to 1960 and going through today, we can see, we have some pretty good wet periods. The dry periods aren't too bad. Really good wet period in the early 80s. We have some dry period in the late 80s. Gets kind of wet for a few years. We have a really good wet period here, the late 1990s. And then boom, starting about 1998, we have a big drought in both climate zones. Again, this is -6, and this is the Eastern Snake River Plain. So, and we have multiple years. There's not even any breaks in here. It's really dry. Have a few wet years, and then we kind of drop back down. And again, this extended multi-year drought, kind of wet. They don't track well. In 2006, we drop into another pretty long period. We get some rain up in the mountains, but the Eastern Snake Plain, the southern part of the county, stays pretty dry. So you can see that we've been kind of hopping back and forth. But this last winter, and we start dropping off again. This is probably -5 drought. So we're starting to get dry again. So this 1995, this is the period of the most recent IDWR model. So the model period starts off with some really wet years and then kind of goes back to capture some of these really dry years. Again, I'm going to skip over these. Okay, so what does this mean? Being a geologist, I kind of like to look at the long view. So the climate models divide the Earth's surface up into a bunch of latitude and longitude boxes, and those are basically their model cells. There's 3 of these cells in Idaho. There's one kind of here in the Central Mountains, and we have Southwest Idaho and then Southeast Idaho. So Cook and others basically used tree ring data. They looked at fossilized pollen, primarily in lake beds. They looked at some of the preserved microfossils in these lake sediments, ash beds, things like that. And they were able to reconstruct the PDSI on a yearly basis all the way back to the year 0. Okay, so that's what these blue lines are, the actual PDSI. I threw a 25-year moving average on this to actually be able to see better what's going on. So again, this is the Central Mountains. So we see, we've got pretty long stretches of dry weather. We have a stretch here that's really dry for extended period of time. We have some wet years up here, then we drop off into these dry periods, some wet years, dry period. So we kind of seesaw back and forth. Okay, here around the year 1000, we see a pretty deep extended drought. We have some wet years, another pretty long period of drought. And, we get into here where we have another long period of drought. Some of you all have heard of the medieval warm period. And, we're basically talking about this time period in here. So we kind of go back and forth. So we get down here, and I can't actually, let's see, there we go. We get to 1900, we get to about 1900, and we see a pretty good wet period in here. This dip is the drought of the 30s. Well, one thing that, Cadillac Desert is getting kind of dated, but one thing he points out is that the water in the Colorado River Basin was appropriated based on the stream gauge records from these early years of the 20th century. You can see that historically, this is a pretty long, pretty wet period. Again, this is the 30s, and then we kind of go up to 2000. So, these graphs look pretty much the same. But the point that I want to make on this is that the industrial age didn't really start here until about 1800. So fossil fuels didn't come into play into this last part. But this early part, which are natural conditions, we see that long-term severe drought is natural. We don't have to, we can't invoke climate change to explain these long drought periods. So those of us that live in the West, have to maybe think that long-term extended deep droughts are a natural part of the climate system. So again, as a geologist, that's how I look at it. So is global warming, the greenhouse gases playing effect? Yeah, it is down here. But again, naturally, we see these things occurring. So let's see.
Jim, just a quick question on that previous graph.
Yes.
So the top graph is blue, the middle one is reddish, and the bottom one is kind of green. What can you tell us? Can you tell us just a little bit about the differences there?
They all track more or less the same. I mean, if we go to the same thing about 1100, this is blue is the Central Mountains, and we can see that we've got here. This is the southwestern Idaho. We can see that it's a little bit longer wet period up here. And if we look at the eastern Snake River Plain, we can see that it's longer than in the mountains, but it's a lot weaker signal. So I mean, by and large, they have the same shape, but there are little differences. One thing, for instance, we see in the 30s, we see this dip in the mountains, and we see it in southwestern Idaho, but it's not not nearly as pronounced over here in the eastern Snake River Plain. Now, part of that may be because of the types of the data that he was working with. And I mentioned pollen, I mentioned tree rings, I mentioned, stuff dug out of the lake sediments. I know, if you read this paper and go into detail in the appendices, I know that there was an Engelmann spruce up at Galena Summit that they were able to extend the tree ring record back to, I think it was like 1521, something like that. So, some of this variability is probably a result of whatever data sources were available in those particular grid cells. So does that answer your question?
Yep, absolutely. Thank you very much.
Okay, so where are we on climate? Well, we've all heard of the El Nino Southern Oscillation, or ENSO, and this is basically a recurring climate pattern, and it's linked to surface waters across a large swath of the tropical Pacific Ocean, warming or cooling by anywhere from 2 to 5 degrees from normal. And again, this can be 2 to 5 degrees above normal or 2 to 5 degrees below normal. And the cyclicity on these things, there's about 3 to 7 years. So there's 3 states in the ENSO, and this is what we're all familiar with. So there's an El Nino where the water, the ocean surface in this area warms, and the La Nina is when it cools, and then neutral is when it's pretty close to normal. So basically, the greater the temperature difference or departure from this normal, the stronger the effect. So we talk about strong El Ninos or weak La Ninas, whatever. Okay, so in a typical El Nino pattern, and we can see I've put Blaine County here with this little star. In a typical El Nino pattern, we see the northern part of the United States and Canada and up into Alaska typically is warmer than normal. And typically the ENSOs are effects are most pronounced in the winter. Okay, so in an El Nino winter, we would expect to see it slightly warmer. The Southwest and the Eastern United States tend to be wetter. And then this area kind of centered on Tennessee tends to be a little bit drier. Okay, and you can see we're right here on the edge of this effect. Okay, so if we have a strong El Nino, we do tend to see this warmer winter with less snow. But in a weak El Nino, we may not see any difference whatsoever. This kind of orange area may shift to the north of us. So in a La Nina, we see the opposite. We see, this area up here tends to be colder than normal. The Pacific Northwest tends to be wet, and the southern tier tend to be warmer and drier. And this area centered on Tennessee, tends to be wetter. Well, again, we are right here on the edge of this wet area from the Pacific Northwest in this colder area in the northern part of the United States. So in a weak La Nina, we may not see any effect. In a strong La Nina, we'll get the wet, cold, snowmaking years, okay? So right now, we're just coming off a weak La Nina. Okay, so these forecasts are done in 3-month blocks. So right now, this forecast was run in April. So the projections, this is for May, June, and July. So all of these different lines are the various assorted climate models. And you can see that there's 24 models here. Many of these climate models are what they use to forecast, to do the climate forecast that we'll talk about in a bit. So you can see that there's a pretty wide envelope of predictions. But if you look at kind of the consensus, which is this blue line, if we look at this consensus seems to suggest, okay, so this is September, October, November, that we're dipping off into another weak La Nina next winter. See, right now we're near neutral conditions, but if this holds true, we may be looking like another winter just like this one. But again, it's a prediction. It's a forecast. We don't know. It could be we could go into a El Nino. We could stay in neutral conditions. It could even go into a strong La Nina. So, but this is kind of what they're seeing. So if we look at the 3-month outlook from NOAA for this summer, just for this summer, basically we see Idaho, and these warm colors are, this is temperature, are basically showing predictions of warmer than average. So we're in this zone that's 50 to 60%. So right now they're saying that the 3-month outlook that we're going to have a 50 to 60% chance of being a warmer than normal summer. Again, this is a forecast, so who knows? But this is when they start talking about a dry summer and a bad season. These are what they're referring to. If we switch to precipitation, again, Idaho is pretty much in this zone of the 40 to 50% probability. So according to these 3-month forecast, we're looking at a 40 to 50% chance of having a drier than normal summer. So again, this is what the emergency preparedness people are starting to get alarmed about. And I put URLs for all of these at the bottom of these slides. Okay, so that's pretty much where we're at now. So where are we going in the Wood River Valley? Okay, so if you think back to a few slides where I showed on the long-term PDSI, I showed all those dots. Those represent the various assorted model cells that the various assorted climate models do the prediction for. There's something called downscaling, and you can go to this website. So instead of seeing the data for this cell, basically you can enter a location. I entered Blaine County, and it will kind of take all those adjacent model cells and then average them into something for a specific locality. So here we are in 2000. So if we look at the predictions from 2000 out, okay, so kind of that envelope defined by the range of the climate runs that we looked at in the La Nina prediction. That's essentially what we're seeing. That's what we're seeing with kind of these shaded colors. The blues are the lower emission scenario. The red is the higher emission scenario. So in other words, if we keep doing what we're doing, we're going to see it in the red. If we actually are able to get a handle on things, this is the blue envelope. Well, this red line and this blue line are the averages of both those scenarios. So what does that tell us? Well, we're popping along at say six inches a year precip. Well, they're not predicting much change in our precip under the future climate scenarios. I think it's because Idaho is kind of on the edge of those effects, like we looked at for the El Nino La Nina. We're just kind of in this intermountain zone that's, just not a lot's going to happen. However, if we go to the climate predictions for looking at temperature, as you can see, we've already started going up since the 50s. And again, if we don't do anything, I mean, they're showing, just looking at the average, they're showing, about 10 degrees of warming under the worst scenario. And, I don't know, a few degrees warming, maybe 5 degrees warming under this better scenario. Okay. So this one is a lot more to worry about. So why would we worry about this? Well, first of all, if it's warmer, we start seeing a lot more precipitation fall as rain instead of snow. And, already, some basins like the Weiser Basin, it's what we call a rain on snow basin, where it's low enough that you get this snowpack, and in the spring you get rain on that snowpack, and all of that snow comes off in a hurry. That's why the Weiser is so prone to flooding. Well, under a warming scenario, we may start seeing something like that in the Wood River Valley. Also, here in the Wood River Valley and in the West in general, we've had this wonderful situation where it snows in the mountains all winter. We get this beautiful snowpack. And in the spring and the summer, it slowly melts, and that gives us our water for the irrigation season. Well, you know, we're, even back in the early 2000s, somebody in our office published a paper saying, looking at all the gauges and stream gauges in Idaho, and they could see that water was starting to come off 2 weeks earlier, even back then. Well, now that everybody's gotten into the act and they're looked at a lot more stream gauges and a lot more people with more sophisticated tools, I mean, actually that 2 week earlier runoff has been increasing. So, especially here in the Wood River Valley, we don't have any reservoir storage above us. So, we may get to a situation where the people that rely on surface water for irrigation, they're going to run out of water earlier than they would have in the past. So, does that mean 1 or 2 alfalfa cuttings instead of 3? Possibly. The people below Magic Reservoir are in a little better shape because they do have a reservoir. The Boise Basin and the Payette Basin, they've got good reservoir storage. But still, if we have these drought scenarios and Magic Reservoir only fills completely every few years, I mean, this is where the main problem is going to come. And we're going to start running out of we may start running out of irrigation water earlier in the season. So with that, I am pretty much starting to get out of my depth. So again, this site with the downscaling is the website is there. So with that, let's see. I'm going to finish on this slide and just kind of make the point, that science can only provide the facts, and this is from a paper that Bill Cunningham and I did a number of years ago on groundwater depletion. So as with any natural resource, there's going to be consequences when you use that resource. So, it's society's job to decide how much consequences we can take. And in order to have these informed scientific opinions, we've got to collect basic data over these long periods to be able to observe them. So that means long-term stream gauges. That means measuring water levels in wells over a long period of time. So coming back to that earlier question about how much water is in the aquifer, well, I can sit here and we know this, we know the volume, the size and shape of the aquifer system in the Wood River Valley. We know the porosity and permeability. We know, what the saturated thickness is. So I can sit here and sketch out an estimate of how much water is in the aquifer in the Wood River Valley. It's really easy. You can do that just like you do estimates of oil reserves. The problem is we can't use all of that water. Nobody in the valley, and certainly, the people of the state of Idaho, if we pump the aquifer to use all of that water, basically we're going to dry up all the streams in the valley, and nobody wants that. I mean, that's a completely unreasonable outcome. So, we may have all this water in the aquifer, but for all intents and purposes, we can't really use it. Now, places like Southern Arizona, the Tucson Valley, they're pumping water that's basically 20, 40, 50,000 years old from the past glacials. So, in the early part of the last century, they dried up their rivers. So, all those big arroyos you see in Tucson, those things were originally arroyos or were rivers around the turn of the last century, but they pumped groundwater so much that they did dry up the rivers. So at any rate, that's, I hope that answers the question as to how much water is in the aquifer. Is, basically until we dry up the stream, until we start affecting the streams, that's how much water we have. So here are some websites. This is the USGS website for Idaho. If you go there, you can see pages about the work that we're doing in Idaho. And you can get to the real-time stream flow data and groundwater level data as well. USGS publications are at this address. And here, if you hold your smartphone up to the screen, this is a QR code that takes you directly to the real-time stream flow site, where you can see a listing of the 290, whatever it is, stream gauges in Idaho that are real-time, including the ones in the Wood River Valley. So with that, I'm going to stop. I hope that helped. I hope I made sense. Let me know if you have any questions.
Jim, let's see, where did it go? I think Jose David sums it up for all of us. Absolutely fascinating. And thank you. Someone else says, great, thanks for a very informative presentation. Thank you also for all that you have done for us here in Blaine County. That was from Niels Ribby. Someone else, this was a fabulous talk. Many thanks to Jim. Other words of thanks for you for this talk in particular. I mean, this feels like kind of a summation of your career that you're sharing with us here in the Wood River Valley. I mean, here in caps, wow, amazing information. Thank you, exclamation points. So anyway, I think you can appreciate how much we have enjoyed this talk. You've taken incredibly complicated information and presented it to us in the most fascinating graphs and charts and images and models. And this talk will be very lightly edited and uploaded onto the Haley Public Library website. And I'm sure it will be used as a resource for a long time to come. So I thank you very, very much for your career and for this particular talk. And thanks everybody. I know we ran over a little bit tonight, but it was worth every second of it, I think. So anyway, thank you all very much for joining us tonight.
There was an equation that they developed in the Kansas-Arkansas River battle stuff that two civil engineers developed called the Glover-Balmer equation. And it only worked right there for the Kansas-Arkansas thing, but it was all people had. So it was applied all over the country. So, once we started getting, computers and computer models, I mean, it's allowed us to do that. Yeah, and again, Idaho and Colorado are on the forefront of this. I mean, we're very fortunate.
Oh, that's good. That's great. I thought it was rather astounding that it's like, well, where does the stream water come from if there isn't a connection between the two? So, but you're right. Data is what gives us the tangible numbers that we can use for information, for conclusions. Thank you very much. It was great.
Oh, I see that question. Ask Kevin.
Hold that question, Melinda.
And to a certain degree, they are treated the same way. When you drill a domestic well, basically you get an automatic right. You don't have to have a permit. That gives you the right to irrigate a half acre, just a half an acre. So, for irrigation wells or irrigation right, I mean, you actually have to apply for a right and get for a right. So I mean, essentially, they are still part of that whole water rights administrative system. Again, ask Kevin.
The question was, why is irrigation water treated differently than domestic water? Isn't water water, and shouldn't it be lumped together? So do we have any other last minute questions before we sign off for the evening? Go ahead, Mark.
Unmute.
I'm unmuting. Thank you, Jim, for all your work. It seems to me that probably the best, smartest thing for residents and water users that USGS along with Water Resources did probably 10 years ago was to require the monitoring of water use on public systems and on private systems, but mostly public systems, so they could use that data not only to support their water right, but to monitor what type of consumption the upper Wood River Valley was doing to Richfield and the downstream users that had senior water rights. So I guess my question from the residents of the water systems that I manage is that when are they going to shut off my water? And you're delivering information to Water Resources so they can determine where it's going to go. But the other question is if we shut off all the consumptive use down in the Bellevue Triangle, is that going to affect Silver Creek? If it were converted to build out for all residential homes that don't have any lawns, would Richfield, I know you couldn't change this, but Richfield and the downstream users be happier because you're not using water for consumptive rights, you're recycling water in the Wood River Valley for them to be using?
Well, I mean, you could certainly run a model scenario and assume no consumptive use in the triangle. I mean, that's something that the model could be used for.
Mm-hmm.
But Silver Creek is complicated. We know that the flow and all those tributaries to Silver Creek bump up in the spring when the irrigation canals are filled. So, to a certain degree, agriculture is supporting the flow of Silver Creek. So, it's complicated.
Are most of those flows into Silver Creek are uncontained flows?
There's really no surface. Well, there's one or two minor ones, but really there's no surface water. I mean, there's no direct surface water connection from the Wood River or the canal system to the Silver Creek system. Again, sometimes there is in one or two places, but by and large, all of that is groundwater. Those are the flow, and all those come from springs and seeps.
Thank you.
So Jim, I just wanted to double check. You said that basically all the flow from Silver Creek comes from those springs, which come from underground water.
Yes.
Is that correct? Okay.
Yeah, in the summer, when irrigation is going on, I mean, there's different ways things are plumbed, but that's true for at least for most of the year, and in one or two places.
So I think that was a wave goodbye. I think we should probably wrap it up.
Thank you.
Dick, did you have a question you wanted to ask? I noticed you were lingering long. You're sure welcome to. If so, you'll need to unmute yourself. So being typed, using the current model, when will Silver Creek run dry?
Not touching that one.
Okay.
I mean, there's too many variables. The question itself, it depends, it depends, it depends, it depends, it depends, it depends. So, I mean, you could gin up a model to examine that question, but again, I mean, just there's so many factors that influence the flow of Silver Creek that, you know, it's a hard, you really can't answer that question.
Well, okay.
Jim,
Thanks,
I just wanted to say that we had somebody on the call, or I guess he's still on there, under the tile John's iPad, and he says, "Thank you, Jim. I managed the D45 canal. Great information."
Well, you know, we've had a house in Bellevue for years, and we've now moved up here full time. We're getting a house in Haley, so I will see all of y'all around as neighbors. And if you see me and I don't recognize you and run the other way, feel free to ask me any questions.
Great. All right. Well, we'll call it quits with that. So thank you once again for your presentation, and everybody for your excellent questions. And we'll hopefully see you next time, next week, for Kevin Lakey. So until then, take good care.